Analysis of frames and machines. Frames are structures made up of elements like beams, columns, and slabs, commonly used in structural applications. Examples include the three-hinged arch, used in bridges, and building frameworks, comprising beams and columns. Machines are mechanisms that convert input forces into output forces. Examples include forklifts, lifting heavy loads, hydraulic jacks, amplify force to lift heavy objects, power steering systems, ease steering, and pulleys, lift or move loads. Basic concept. If a frame is in equilibrium, then any member of the frame is also in equilibrium. For the frame in question, the following steps are used. 1. Draw the free body diagram. Start by drawing the free body diagram of the entire structure. Use equilibrium equations to determine the reactions at external supports. 2. Separate the structure into members. Separate the structure at the pins into individual members. Draw the free body diagram for each member. Note that internal reactions at pin B are equal and opposite for each member. The pin reactions are also equal and opposite. 3. Apply equilibrium equations. For each member, apply the equilibrium equations to determine the unknown reactions. The equilibrium of the member AB. 2. The moment about B, we obtain the XA. 3. The equilibrium in the X direction, we get XB. 4. The equilibrium in the Y direction, we obtain YB. The equilibrium of the member BC. 5. The equilibrium in the X direction, we get XC. 6. The equilibrium in the Y direction, we obtain YC. To summarize the steps for analyzing a frame. Start with the equilibrium of the entire frame. Begin by identifying a single equation with only one unknown YA in this case. Separate the members, find the solutions accordingly. Determine the horizontal and the vertical components of reaction at pins A, D and F in the three-hinged arch shown. Notice that the external supports are not aligned, but one member, AD, is horizontal. For this case, to analyze the frame, dismember it into two separate members. Create the free body diagram for each member. Note that the forces at pin D have equal magnitude but act in opposite directions. Start with the equilibrium of member AD, the horizontal member. 1. Using the equilibrium moment about point A, calculate YD. Analyze member DF. After determining YD, member DF will have only three unknowns remaining. 2. Use the equilibrium moment about point F to calculate XD. 3. Use the equilibrium forces in X direction to calculate XF. 4. Use the equilibrium forces in Y direction to calculate YF. Back to the equilibrium of member AD. 5. Use the equilibrium forces in Y direction to calculate YA. 6. Use the equilibrium forces in X direction to calculate XA. We observe that the analysis of a three-hinged frame involves 6 unknown force components and 6 independent equations. It is crucial to begin by identifying an equation with a single unknown, as this simplifies the analysis. This approach is typically applicable when two pins are aligned either vertically or horizontally within the entire frame or in its dismembered members. Take note of the order of steps in our analysis, as it helps minimize the time required to solve the problem. In this example, we introduce a pulley and a two-force member. We will learn how to handle a pulley in a frame and how to analyze a two-force member. The problem. For the given frame, find the reactions at supports A, B, C, and E. Step 1. Free body diagram and reactions. First, draw the free body diagram of the entire frame and use the equations of equilibrium. There are three unknowns: the normal force at A, and the horizontal and vertical forces at C. Taking the moment about point C gives the normal force at A. Using equilibrium in the horizontal direction gives the horizontal force at C as negative of the normal force at A. Finally, using equilibrium in the vertical direction gives the vertical force at C. Step 2. Simplify the pulley. To simplify, remove the pulley and show its effects on the frame. The pulley is fixed to the frame at point F, and the cord is attached at point G. When removing the pulley, add the reaction forces at F for both the frame and the pulley. These reactions are equal in size but opposite in direction. The tension in the cord is the same as the tension in the frame at point G. Remember, the cord can only handle tension. Step 3. Pulley equilibrium. From inspection, the tension in the cord is 1000 newtons because the pulley is smooth. This means the horizontal and vertical reactions at F are also 1000 newtons each. After this, the pulley can be completely removed. Step 4. Two-force member. Member CDE is a two-force member because it has two pins and no forces acting between them. Separate this member and assume it is in tension. Note that the forces TEC in points C and E are equal and off-site of the assumed tension in the two-force member EC. Now, the frame is simplified as shown. Step 5. Simplify the frame further. Separate member ABC and add the reaction at B for both members. These reactions are equal and opposite. The simplified diagram is ready. Step 6. Choose the simplest member. To make calculations easier, choose the member with fewer forces. In this case, it is member BFE. Step 7. Solve for member BFE. Take moments about point E to find the vertical force at B. Use equilibrium in the vertical direction to find the force two-force member TEC. Finally, use equilibrium in the horizontal direction to find the horizontal force at B. Subscribe to this channel to stay updated with more videos on engineering mechanics. Your comments and feedback are always appreciated.